In 1968, 7 countries were operating satellites in orbit, while only 3 countries had the ability to launch one themselves. But they were on the verge of being joined by a Canadian university. Starting in the early 1960s, Montreal, Quebec-based McGill University developed and began testing an ambitious concept to place small satellites in orbit. It was the High Altitude Research Project and the Martlet Orbital Launch Vehicle. The idea of using guns to achieve super high altitudes goes back to 1865, when Jules Verne published his book From the Earth to the Moon. Many groups have subsequently explored high altitude shots from larger and larger guns. What differentiates the HARP project from anything else before or since was the ambition of its designers and the sheer scope of the project. Their ultimate goal was an advanced satellite launch platform loaded into a giant gun. While not an ideal way to put people into space, today's CubeSats and microsats could be easily launched at a fraction of the cost of traditional rocket platforms. It was the lifelong ambition of one eccentric genius, and his story is inextricably linked to the concept: Gerald Bull. Gerald Bull was an exceptional person in all respects. Born in 1928 in North Bay, Ontario, he entered the University of Toronto at age 16, and by 1951, age 22, he had completed his PhD. This earned him the distinction of being the youngest person to earn a PhD from a Canadian university. Even before graduating, he was recruited by CARD, that's the Canadian Armament Research and Development Establishment, where he began working on the Velvet Glove missile. Check out my video about the Velvet Glove, where I go into lots of detail about its context and development. His work there focused on developing an inexpensive substitute for a supersonic wind tunnel. Bull's PhD thesis, after all, was about supersonic wind tunnels, and he knew how important their absence would be to the success of the program. To solve the cost problem, he flipped the whole thing on its head. Instead of pushing air past a stationary model, models would be shot out of a gun at high speeds. Their flight paths would be recorded through witness plates made of paper sheets. It was a clever technique and allowed the project to move ahead more quickly and gather critical high-speed shockwave data. Unfortunately, research into the Velvet Glove ended in 1956, when the focus of CARD shifted towards anti-ballistic missile research. To fulfill the new need at CARD for higher hypersonic speeds, Bull started researching novel gun designs, culminating in the 3-step light gas hypersonic gun. This work was used to study the infrared and radar cross-sections of hypersonic projectiles as part of a joint Canada-UK research program. In 1957, Bull began to get involved with high-altitude research using gun-launched atmospheric probes. He wrote a paper in the fall of 1959 about the capabilities of vertical probes that caught the ear of the US Army Research and Development. They arranged for a copy of Bull's 5-inch gun concept to be installed at the Aberdeen Proving Grounds in the US state of Maryland for testing of his subcaliber shell designs. The US Army's ballistic research laboratories would help to develop optimized projectile designs for the 5-inch and later 7-inch guns. This partnership would prove to be very fruitful over the years. While working with Dr. Charles Murphy from the Aberdeen site, the two came up with the idea of using the gun to study supersonic shock cones. Bull used this technique while briefly working on the Avro Aero project. His work identified an instability with the Aero supersonic shockwave. This necessitated the creation of the complex stability augmentation system to correct the issue. Bull's work at CARD came to an abrupt end in 1961 over a disagreement with his supervisors. Bull was widely known to have a short temper and was a bit of a narcissist, to say the least. He had a habit of calling anyone who disagreed with him cocktail scientists. This, plus his disdain for authorities, would come back to bite him in the ass time and time again. While his temper was a concern, he was a very charismatic and articulate communicator. This endeared himself to many people, and he would gain enemies and allies in equal measure. Luckily for Bull, at that time the faculty at McGill University was dramatically increasing the size of their engineering department. They wanted to become a world leader in aerodynamics. Bull was a perfect fit, and he was welcomed with open arms. It wasn't long before he began to advocate for a gun-based atmospheric research project. All the work in his career up to that point had been preparing him for that goal. He formed a small team and proposed using subcaliber gun-launched projectiles to reliably send suborbital payloads to altitudes up to 200 kilometers, in order to study the physics and chemistry of the upper atmosphere. There was, however, some competition in the suborbital field coming from another Canadian project, the Black Brant sounding rocket. It had started a few years earlier with the full support of the Canadian government and was already making flights past 200 kilometers. Check out my video about the Black Brant series if you want to know more about this amazing project. Link in the description. Bull pitched his gun concept as being fundamentally cheaper and more reliable than rocket-based concepts. With a gun, the propulsion for the entire flight is expended upon launch. That way, a projectile doesn't need to carry any unnecessary propellant weight as it climbs to apogee. The barrel also stabilizes the projectile as it accelerates, and once it leaves the barrel, aerodynamic forces keep it on target. This results in a much more predictable, more repeatable flight path. In other words, the HARP gun could send a payload to the same patch of sky over and over again, enhancing its scientific benefits. Plus, there was the potential follow-up technologies, like rocket-propelled multi-stage orbital vehicles. This was Gerald Bull's ultimate goal, after all. I won't go into all the funding details, but to say that it was a mess. McGill covered the initial costs under the assumption that the Government of Canada would pick up the project and pay them back. This didn't happen until the Americans came to the table. Part of the government's hesitation was around the duplication of programs. The Alouette satellite was preparing to be launched in 1962 on board an American Thor Agena rocket. Check out the video I made about the Alouette's development and some context about the early Canadian space program. Link in the description. At the same time, the suborbital probe, Black Brant, was being tested and developed. The HARP project fell between these two other, more expensive and prestigious programs. Eventually, and after some heated negotiations, everyone got paid, with McGill remaining in charge of the overall project, and the Government of Canada and US Army sharing the costs. With the approval of this proposal, the High Altitude Research Project was born. It may have been Gerald Bull's baby, but there was widespread interest in it as a research tool. Many scientific investigations were initiated to complement the project and to serve as payloads. These would include atmospheric composition studies, aerodynamics, re-entry and meteor physics, and meteorology, with a particular focus on upper atmospheric wind profiles. Bull's team began to put the rest of the program together. They would need to secure 4 things: a gun, a place to shoot it, something to shoot out of it, and a place to build it. Production and basic testing of the projectiles and gun components would be carried out at a specially built facility in Highwater, Quebec, straddling the border with Vermont. The land was originally owned by the Bull family, but, despite the bad optics, was an ideal location. It lies in a deep valley, providing a natural testing range. Many buildings, such as a production facility, powder magazines, blockhouses, labs, etc., were built on the site. This facility would act as the home base for the project and facilitate cooperation with the US by allowing easy transportation of equipment across the border. The US Army installed a 16-inch smoothbore battleship gun there to fire horizontally. It was used to test different propellant configurations and examine the gun exit physics. This informed refinements to the sabot and pusher plates, helping to ensure a successful flight. Its close proximity to the university and production workshop meant that new designs and refinements could be tested quickly. Where to actually launch the projectiles was simple. McGill already had a couple research stations in Barbados, and the government there was extremely supportive. It was an attractive location for HARP because of its vast followed area over the ocean and its proximity to the radar tracking systems in Cape Canaveral, Florida. Not to mention that it's pretty much the best place to have to go for a work trip. Barbados was eager to host HARP. It gave well-paying technical jobs to over 60 of its citizens, provided much-needed foreign investment, and put the tiny island on the high-tech map. A site was chosen close to the Sewell Airport, now called Grant Lee Adams International Airport, where local workers began construction of the gun mount, as well as various outbuildings including powder magazines, sensor mounts, and blockhouses. Bull then used his contacts in the US military to secure their interest and material support. This came in the shape of gun components and range equipment. The American Ballistics Research Laboratories contributed several radars for tracking projectiles, while the US Army prepared another battleship-style 16-inch smoothbore gun, complete with a shore mount. The trick was getting the huge barrel into position. The beach near the launch site was unsuitable for landing a heavy 140-ton barrel and 90-ton mount, so instead the beach at nearby Foul Bay was used. This necessitated the construction of a temporary 2.2-mile railroad that was completed by local Barbadians. By January 1963, the gun and its components had been installed, and test shots using metal slugs were made to prove the system. Now that they had a gun and a base of operations, it was time to build a projectile. The Martlet 1 was the first sub-caliber projectile made for the 16-inch gun. Its main goals were to prove the viability of the system and identify those areas where more engineering research was necessary. Its name, Martlet, was a nod to the mythical footless bird that makes up part of the McGill crest. The Martlet measured 1.8 meters in length and had a diameter of 127 millimeters. 4 fins stabilize it in flight. The fact that it's sub-caliber means that it's a much smaller and lighter projectile than was originally intended for the gun. This results in higher muzzle velocities, higher altitudes, and greater ranges. To stabilize it in the gun barrel, a 4-pedal plywood sabot surrounds the main body. The base plate, made of steel and plastic, seals the gun barrel and provides impulse to the projectile. The flight profile for a high-altitude shot was simple. The projectile in its sabot was hydraulically rammed into the gun barrel, followed by bags of propellant. The barrel was raised to 80 degrees and fired. Upon leaving the barrel, the sabot pedals and pusher plate fall away, leaving the projectile to follow a ballistic trajectory. It would splash down in the ocean somewhere near the southeast coast of Barbados. This fact led to an interesting debate about the legality of the entire project. By convention, space projectiles were registered in order to cover liability in the case there was an accident. Trouble was who should register it. It wasn't an official Canadian project, but rather that of a university, so they passed the buck on to the US, who provided the majority of the funding. They declined responsibility because it wasn't under their direct control. Responsibility then turned to Barbados, who was in turn a territory of the UK at the time. Ultimately, this meant that the UK would have been responsible for any damages caused by a Canadian university's American-funded research project taking place in one of their territories without their permission. A challenging legal stance, no doubt, but one that was ultimately solved by not registering them at all and assuming everything would be okay. A risky strategy that, in hindsight, worked out just fine. The only distinguishing marks on them were the name of the shot stenciled on the side. The Martlet 1's first vertical launch was in early January 1963, when 2 were launched. This effectively proved the concept and equipment. Now focus could be moved onto the next generation. The Martlet 2 was a series of glide vehicles that explored different payloads, materials, and weight distributions. These would be the scientific workhorses of the program, and altitudes between 100 and 150 kilometers were routinely achieved. To further increase altitudes, efforts were made to make the sabots and pusher plates lighter. This, in combination with aerodynamic refinements, would improve its ballistic coefficient and make them fly higher. There were also many improvements that could be made to the gun. I won't go into the details about the breech pressure and muzzle velocity advances, but to say that a significant portion of the total resources of the project was spent perfecting it. Higher muzzle velocities directly translate into increased altitude performance. There were 2 ways to do this. One is to make the barrel longer. This increases the time the projectile can be accelerated by the gas. The other is increasing the breech pressure, either through using more propellant or changing how it's ignited. Essentially, this involves maximizing the pressure behind the projectile while keeping the gun from exploding. The first of the series, the 2A, was produced primarily as a high-altitude balloon ejector. These balloons would then be tracked by radar to determine wind speed and direction in the upper atmosphere, a highly desirable scientific measurement at the time. The balloon was kept in the bottom of the body and ejected by a timed explosive charge. This would occur at altitudes between 85 and 100 kilometers. Lead ballast was carried in the nose to maintain the correct center of gravity. It first flew in June 1963. Martlet 2B was the name given to a pair of special payloads. One was an explosive acoustic charge for measuring shockwave propagation, and the other was an explosive pellet device to study meteor re-entry physics. Both were launched in the August 1963 series. Not all launches were successful. In fact, almost half failed, usually due to some kind of malfunction in the gun or aerodynamic troubles. These would be slowly corrected as the program progressed. The August 1963 series was also the beginning of the exploration of rocket-boosted payloads as another step towards developing an orbital system. The Martlet 3 series was essentially a two-stage rocket, stage 1 being the gun, and stage 2 being the rocket motor. This promised to bring a smaller payload to a much higher altitude. The goal was to gain the same amount of impulse from the rocket as it did from the gun. The rocket motor had an open cylindrical core, which provides optimum performance for a solid motor. Testing at the high water facility began in August 1963, but showed failures with the rocket motor. The 3A's rocket motors were not ignited so they could be examined after recovery. Significant grain deformation due to the incredibly huge accelerations at launch were noted. The Martlet 3B improved on the 3A. They switched motor styles from core burning to end burning to solve the deformation problem. Trouble was that end burning isn't the best configuration because it produces lower thrust and longer burn times. The airframes were also thickened for added strength, and the number of fins was increased to 6. Aluminum sabots were tried in the 3B series in place of the heavier plywood ones. These tests were centered around trying to perfect the propellant style given the extreme G-forces experienced at launch. It was found that filling a core burning motor with a fluid of equal density to the grains allowed it to handle over 12,000 Gs. The fluid was allowed to drain out of the motor before ignition. A number of 3B motors of both varieties were successfully ignited immediately after launch. Flights were modest compared with expectations, and only a few managed to break the 150 km mark. 2 advanced variants were built later in the program. The Martlet 3E was a 7-inch full-bore model that featured a fiberglass airframe. 5 launches took place at high water and were recovered on Lac Saint-Pierre for examination. The Martlet 3D was a 16-inch full-bore rocket. 5 horizontal launches took place in the spring of 1966 at the high water facility. These were the largest rocket motors ever shot out of a gun and would later become the first stage of the proposed Martlet 4 satellite launcher. The December 1964 series would see the next generation of glide vehicles tested in a new gun configuration. The barrel of the 16-inch gun was initially extended by 6.7 meters, but this proved unstable, so it was decided to instead bolt on a 15.5 meter extension, doubling its length. This dramatically improved the gun's performance. A longer gun barrel meant more time to accelerate, lower G-forces, higher muzzle velocities, and more efficient use of the propellant. The Martlet 2C series was an improvement over the 2A and would prove to be the workhorse of the entire HARP effort. It was designed to release chemicals, called TMA, capable of producing a glow trail that could be tracked by observers on the ground. The liquid TMA payload was ejected by a piston extended by compressed nitrogen. The airframe was better designed to withstand the 25,000 Gs of acceleration it was expected to encounter in the gun barrel. The main body was made from stronger Meraging steel and was tapered in the exterior aft body. The 2C was able to routinely achieve flights between 125 and 150 kilometers altitude. Another interesting design feature was that its high-pressure TMA payload could be loaded while the projectile was loaded into the gun. This helped to prevent any handling hazards from the exotic chemicals. The harmless compressed nitrogen was loaded through a side port prior to entering the gun. Hundreds of 2Cs would be flown to gather wind data in the upper atmosphere. The 2C Mod 2 and Mod 3 series were instrumented vehicles to test electrical components. One was to measure the internal temperature of the vehicle throughout its flight, and the other was testing the electronics of a sun sensor. These payloads also included transmitters that relayed telemetry and measurement data from launch until they impacted the ocean. Later in the program, Langmuir probes were also developed and flown. These were used to determine electron temperature, electron density, and electric potential of plasma in the atmosphere at high altitudes. The 2C Mod 3 series was designed to deploy chaff that would reflect in the S and X band radar frequencies. Another instrumented vehicle, the 2E, was also based on the 2C and was used late in the program to test the attitude sensor and control units for the 2G1 and 4 models. The Martlet 2D series was an enhanced 2C with double the payload capacity. Its size was increased and its aerodynamics were greatly refined. Only a handful of launches were made starting in March 1965 before the follow-up 2G version was ready. The Martlet 2G series was the ultimate incarnation of glide vehicle development. Starting in 1966, the 2G was built and tested at the high water facility. It differed from the others in that its tail section was tapered instead of the traditional flat bottom design. This improved the aerodynamics and was made possible due to a redesigned sabot. The new one was placed around the center of mass instead of at the base. Because of this, the bottom of the vehicle would be exposed to the hot gun gases during launch, but this had little effect on its operation. It was predicted that altitudes of up to 200 kilometers could be achieved with this system. It should be noted that a copy of the Barbados gun was also installed at the Yuma Proving Ground in Arizona. There it fired horizontal shots in support of the high water and Barbados operations. While the massive 16-inch guns were the star of the show, they weren't the only actors. Many other guns were built and used in the HARP project, including 4.2-inch, 5-inch, and 7-inch systems. Most of these were built at American testing facilities, where tracking equipment was already in place. Computing Devices of Canada Limited, the same firm that was providing ignition equipment, loaned the project their first gun. It was a 4-inch naval anti-aircraft gun, which had been smoothbored to 4.2 inches and installed at the Barbados site. It could shoot a 6-kilogram projectile up to 30.5 kilometers. This gun was mainly used to test ignition systems for the powder charge, a topic that turns out to be much more complicated than a layman would otherwise assume. Development of the 5-inch gun began in 1960, with the first gun being installed at the Aberdeen Proving Ground. This was joined by another one at Wallops Island in Virginia. There, the research benefited from NASA's extensive radar system, which were able to track the projectiles, called BRL-5s or Martlet Juniors, throughout their flight. These flights routinely made it up to altitudes of 30.5 kilometers, but this wasn't good enough, hardly an improvement over the 4.2-inch gun. After optimizing the projectile and adding a 3-meter extension to the gun, they were able to reach 73 kilometers. Later in the program, another 5-inch gun was installed at the White Sands Missile Range in New Mexico. The guns were involved in an extensive study of upper atmospheric wind speeds, and data was collected from all across North America. To further this end, guns were also installed at Fort Greely in Alaska, at the Yuma Proving Ground in Arizona, next to the 16-inch gun at the Barbados site, and finally one in high water Quebec. These guns were involved in well over 500 sounding flights, with launches at some sites continuing until late 1968. The 7-inch gun was a scaled-up version of the 5-inch system. A 175mm M113 artillery gun was smooth-bored and extended by 7.9 meters. A 1.6 meter long, 9 centimeter diameter, 27 kilogram projectile, called the BRL-7, was able to achieve altitudes of 91.4 kilometers. Glide probes were the bread and butter of the HARP project. The U.S. Army funded the collection of meteorological data, which brought in a steady level of funding. This, combined with the funding from McGill University and the Government of Canada, allowed Bull and his team to dream big. Their goal with the HARP project began to focus around bridging the gap between sounding rockets and orbital rockets by developing an orbital launch capability. For some historical context, Alouette 1 was launched in 1962, then Alouette 2 launched in 1965 on board expensive American rockets. At the same time, the Black Brant was making suborbital flights over 500 kilometers altitude. The HARP team wanted their system to complement those achievements by providing a cheaper way to place small payloads in orbit. Although the project reported that less than 25% of its effort was placed on developing the required technology, it was the focus of Bull's ambition, and it would prove to be his lifelong obsession. There would be two distinct systems, the sub-caliber Martlet 2G1 and the full-bore Martlet 4. The Martlet 2G1 was a two-stage rocket based on the 2G glide vehicle. A 2.2-meter-long open-core rocket motor took the place of the TMA payload. It would have an all-up shot weight of 544 kilograms, including a 7.2 kilogram orbital payload. In order to go from suborbital shots to orbital, the projectiles would need to go much faster. The optimal launch angle was changed from the 80 degrees for a high-altitude shot to around 55 degrees. Lower than this and the atmospheric drag effects would dominate and degrade performance. Higher than this and the projectile wouldn't have enough horizontal velocity to achieve orbit. After all, getting into orbit is all about speed, not altitude. The launch profile of the 2G1 was fairly simple. The gun would fire and launch it up to an altitude of around 185 kilometers. Above 45 kilometers, the tail section would be discarded. Fixed thrusters would then spin up the vehicle to make it gyroscopically stable now that it has left most of the atmosphere. After 190 seconds coast flight, it would despin and begin to orient itself for orbital insertion. The attitude control system uses a sun sensor and a horizon sensor to fire the attitude control thrusters to orient the rocket stage for ignition. At apogee, it ignites its second stage to bring its speed up from 5,900 km per hour to 28,262 km per hour. Upon burnout, the second stage is separated, and the 7.25 kilogram payload is released to do its thing. Due to this launch profile, orbits are restricted to apogee heights achieved by the gun's muzzle velocity. Tests of the 2G1 were carried out at the high water facility. By 1966, all aspects of the technology had been tested, and it was predicted to be fully operational by 1968. Flights were expected to cost between $10,000 and $20,000 per launch. Plans were also in the work to replace the solid rocket motor with a liquid engine. This would have increased flexibility of the system, but it never made it past the pen and paper stage. Another set of plans detailed a three-stage version, but this too was just a paper study. The star of the entire HARP program by far was the Martlet 4. It was a full-bore, multi-stage orbital rocket for the 16-inch gun system that promised to insert meaningful payloads into low Earth orbit. The pop-out fins, rocket motor, and attitude control system were all tested on the Martlet 3D at the high water facility and were ready for flight. The 8.5-meter-long rocket was composed of 7 components. The first stage was adapted from the Martlet 3D and called the 4A. Above this was the interstage adapter that contained a separation charge and the ignition hardware for the second stage. The second stage was called the 4B. On top of the second stage was another interstage adapter for stage separation. The attitude control section contained a similar system to the 2G1 and was used to spin up the remaining sections and then orient it for the third stage ignition. The third and final stage was called the 4C, and it was used for orbital insertion. A 91 kilogram payload, measuring 40.5 centimeters by 122 centimeters, sat atop the stack. Its configuration was dependent on the mission. The flight profile was similar to the 2G1, but wasn't limited by the gun's performance. The gun would be set to 33 degrees and fired. After leaving the barrel, it would have an initial velocity of around 6,600 km per hour. Less than a second after launch, the first stage would ignite. After burnout, it would separate and the second stage would ignite, bringing it up to a velocity of 21,770 km in only 40 seconds. The rocket would then coast for almost 9 minutes before orienting itself and firing the third stage. This brings it up to its orbital speed, and upon burnout, the payload is released at an altitude of around 680 kilometers. For reference, the International Space Station orbits at 400 kilometers. This profile would have made delivering hard or liquid payloads to a similar space station possible with very low launch costs. Unfortunately, testing of the full rocket stack never took place. By 1967, the program fell on hard times, and there was little funding available for the advanced project. Bull maintained that the high accuracy of the gun made deliveries to a narrow range of orbits very straightforward, and that advances in gun technology could only increase its performance. On that front, Bull and his team had many ideas. The basic motto in gun development is, "Make it bigger." They proposed that the Yuma and Barbados guns be doubled in length and have an enlarged powder chamber. This would have made them 150 caliber guns. Since a barrel of this length and weight is prone to bending, fiberglass barrel extensions were being researched. Propellant ignition was an area of ongoing research. At the start of the program, the tall stacks of powder were ignited from the breech face. Later, they moved to a 5-point ignition system, which greatly improved performance and reliability. The next stage was research into a traveling charge type ignition. This would have better managed pressures within the barrel and further increase muzzle velocities. Plans were also made for a 300 caliber gun. This was the 32-inch gun system. It was projected to cost $1.5 million and would drastically increase the capabilities of the program. Unfortunately, none of these plans became a reality. In 1967, the Government of Canada pulled their funding, largely due to the quarrelsome nature of Bull and the enemies he had made in Parliament. This was followed soon after by the US Army, who were becoming overextended due to the Vietnam War. McGill University couldn't bear the brunt of the project alone, and so they looked to sell it off. Bull purchased the program in 1968 and consolidated the HARP assets into a company called the Space Research Corporation, based at his high water facility. He then gained the backing of the Bronfman family of Seagram whiskey fame. They continued to fund the research until 1970, when the company was able to operate on its own. Bull resigned from McGill in 1969, but continued to work on HARP in Barbados and at high water until 1971. During that time, he proposed a more advanced version of the Martlet 4, called the GLO-1B. It was never built. The HARP project had completely fizzled out by 1971. Gerald Bull then changed his focus to making some money in the arms trade. His company began working on advanced artillery systems. He developed an advanced shell shape that dramatically extended the range of existing guns. These were called Extended Range Full Bore, or ERFB shells. In addition to this, he also improved the M109 howitzer, increasing its range significantly. He called the system GC-45, or Gun Canada 45, and began looking for customers. Canada and the United States showed no interest, nor did other NATO members. Their first customer would be Israel, who bought 50,000 ERFB shells in 1973. This turned out to be a fruitful deal for Bull, as he was offered an American citizenship thanks to the exchange. This gained him access to high-security information, a wise business move. Gerald Bull then made a major misstep. He sold 30,000 ERFB shells, radar equipment, gun barrels, and plans for the GC-45 howitzer to a South African state arms corporation. At the time, South Africa was under sanctions due to their apartheid policy and terrible human rights record. He claimed to not have known it was illegal, but was arrested by the US and sentenced to 6 months in prison, which he served in 1980. He was also charged in Canadian courts for the same crime, but was only given a fine. This experience left Bull extremely bitter, and he vowed to never set foot in or assist Canada or the US ever again. He then moved to Brussels with his wife and 7 children, where he continued to orchestrate sales of the ERFB shell and advanced guns. His life took another dark turn when he was approached by Saddam Hussein's regime in Iraq. They wanted the shells and the GC-45 gun, but they also came with an alluring offer. They would fund another supergun to build on his work with the HARP project. The offer was too tempting for Bull, and he quickly signed up. The Iraqis claimed to want a satellite-launching supergun capable of placing 540 kilograms payload into low Earth orbit. Called the Babylon gun, it would have been 150 meters long and have a bore diameter of 1 meter. Components were sourced from all over the world, but the moves were picked up by the Israeli spy network, the Mossad. They were justifiably concerned with the fact that the gun could also be used as very long-range artillery, and that Bull was helping the Iraqis improve their Scud missiles. These concerns resulted in Gerald Bull's assassination at his home in Brussels on the 22nd of March 1990 by Mossad agents. This extrajudicial killing has never been taken to court, and no one has ever been accused of the murder. When Bull was killed, the idea of a gun orbital launcher almost died with him. A few other projects would attempt to take the place of HARP, but none experienced the same level of success. The Americans followed up HARP with SHARP, the Super High Altitude Research Project. This project studied the use of two-stage light gas guns to achieve higher muzzle velocities. Work started in 1985 and continued until 1995. The gun worked well, but the program was cancelled before a larger version could begin vertical launches. A private company called Quick Launch also tried their hand starting in 2010. Their concept was innovative in how they arranged the barrel. It was submerged in the ocean and supported by buoyancy. This made the device very adaptable and mobile, allowing for a larger array of possible orbital profiles. Quick Launch was unable to secure funding to build their gun. This was largely due to the availability of other space access technologies, like SpaceX, and the company was put into hiatus in 2016. The allure of a space gun remains, and perhaps in the future, someone will convince the right people to make it happen.